So other questions? Also a good question. Okay, so we talked about Lua on Tuesday. Today we're going to talk a little bit more about some more theoretical stuff. We're going to talk about parse trees and how parse trees work. This is going to be the context-free grammar stuff we mentioned. So context-free grammars, CFGs. Usually the way you talk about it is it's delineated into a set of rules. So for example, we're going to have a couple of different symbols on the board. So let's just make one. Let's, for example, say S with an arrow with the number 1 and an S. And then another rule will be S to the 0, like so. There are 3 symbols on the board. Don't worry about the CFG here. But there are 3 symbols on the board here, correct? Besides the arrow. What are those 3 symbols? S,
1 and 2.
1 and 0. Excellent. Those are the 3 symbols. We have the symbols on the left-hand side over here. These symbols over here are called non-terminating symbols. Non-terminating symbols. Non-terminating. This means that the symbols on the left can be changed into things on the right-hand side. So for example, if we start with the sentence S, if that's what our sentence starts as, we want to be able to figure out what that sentence can become. So for example, if we start with S, what's an option for S to become? We can either apply rule 1 or we can apply rule 2. Let's just apply rule 2. If we apply rule 2, we get 0. Is that 0 symbol a non-terminating symbol?
No.
No, it's a terminating symbol. So on the right-hand side, we have a mix of terminating and non-terminating. Mix of terminating and non-terminating. I know it goes up there, but that's what that says. Where the terminating symbols mean that you just stop. You can't continue that any farther. And so by applying rule 2 to the sentence S, we can get the sentence 0, which means that the sentence 0 is a valid sentence, or is a sentence that we can create. When we say that the sentence 0 is a sentence that we can create, essentially what we're saying is, given this context-free grammar, if this is the grammar we're talking about, and I have the sentence 0, that is a valid grammatically correct sentence. That's all it means. I don't know what 0 means. 0 is a terminating symbol. It can mean anything, but for now it just means 0. The reason why we do this is because we want to be able to figure out if sentences are grammatically correct. So let's take a sentence. For example, if I take the sentence 0, 1, 1, 1, 0, is that a grammatically correct sentence? You say no. So give it a second, let other people think about this. Then we'll want to say yes. Nobody wants to say yes. Okay, so why do you say no?
Starts with a terminator.
Starts with a terminating symbol. So you mean which one does it start? This side or this side? The left side, that one? So it starts with a terminating 0, you mean? So the way we want to think about this is, can we generate this sentence from the symbol S? That's the question we want to ask. So the statement you made where it starts with a terminating 0 isn't valid. Because I can turn this into, the 0 is just start. Hey, 0, that's a valid sentence. It both starts and ends with the terminating 0. Correct? So the fact that this starts with a terminating 0, terminating symbol 0, doesn't mean that this is an invalid sentence. Doesn't mean you're wrong. Because you can't generate this sentence. But it isn't valid for the reason that you specified. So can we generate this sentence?
Yes.
Yes? Okay, so how do we generate this sentence? If I start with S,
I row 0, 1, 1, 0.
so how do I generate it? I can only apply these rules. So which rule do you apply first?
Rule 1.
So you apply rule 1. When I get rule 1, I get the 1 and the yes. So this is rule number 1 application.
Then rule 2.
Then you apply rule 2 and you get, what is move this down a little bit. You apply rule 2, and you get a 1, 0. Can you apply any more rules?
No.
No. Is that sentence that sentence? No.
So you cannot.
So you cannot. Are you sure?
Yes.
Have you tried all of them?
Yes.
Ah, so you tried all possible combinations of sentences, right? Now, if you're going, what does it mean? Does it mean to have a sentence? So this 1, 0 is a sentence. This is when we mean it's a sentence, 1, 0. This sentence is 0, 1, 1, 0. 1, 1, 1, 0.
Oh, it can be. In a way, in a how.
Okay. So
So
you say now you're saying that it can be. Well, in this case here, we applied rule 1. Let's look at it a different way. So we applied rule 1, then we applied rule 2. We can also take the sentence and just apply rule 2, correct?
Yes.
Which would give us 0. Can I apply any more rules after that? No, so I cannot, that's not that sentence, so that doesn't work. So let's try another application. So I apply rule 1 because applying rule 2 will kill me, right? Applying rule 2 will kill me. I notice this every time all of a sudden I go, oh, applying rule 2 will end. I cannot do anything after applying rule 2, right? So that'll give me 1s. What rule can I apply now?
1.
I'll apply rule 1 again. That'll give me 1, 1s. Can I apply rule 1 again?
Yes.
Yeah, let's do it again. Apply rule 1 again. 1, 1, 1s.
And 2.
Then apply rule 2. So apply rule 2. That'll give me 1, 1, 1, 0. Can I apply any more rules? No. Is that sentence that sentence? No. Have I proven that I cannot generate this sentence?
Well,
I have not proven yet that I cannot generate this sentence yet. I have demonstrated through 3 examples that I can't generate that sentence. Yes.
I don't really know what's going on right now.
Okay. So we have some terminating symbols on the non-terminating symbols on the left. S, right?
Wait, what is it? What language is this? What's going on?
This is a context-free grammar. We're just making it up as we go.
Oh.
This is how all context-free grammars work. You just have some non-terminating symbols on the left. You have some non-terminating and some terminating symbols on the right. So for example, if I see the symbol S, I can either use, this is a rule 1. This is rule 1 and this is rule 2. I can either apply rule 1 and the S becomes a 1 with an S next to it. Or I can apply rule 2 and the S becomes a 0. Those are the only 2 things I can do. Yes?
And terminating means that stuff can't turn into
Correct.
another thing.
Terminating symbol means it just doesn't show up on the left-hand side. So for example, if I wanted to, I could make another rule that says 0 becomes 2, 5 for whatever reason. And then 0 is no longer a terminating, it's a non-terminating symbol because 0 can become something else. Does that make sense? All right, so we won't look at that one, we'll look at that one in a little bit here. But what we are trying to do is by starting with the sentence S, which is the most general sentence I can make. I say, if this sentence is possible, I must be able to start from the most general sentence. S is any sentence that I can make. That's the assertion, the claim I'm making. By applying the rules onto S, I can generate any number of outputs. How many different kinds of outputs can I generate? How many total possible are there?
infinite.
There's an infinite number of sentences I can generate. So this isn't a finite number of sentences. I can apply rule 1 for an infinite period of time, and I will get an infinite sequence of 1s. So the sentence 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 infinity 1s with a 0 at the end, that's a valid sentence for this grammar. Because this grammar says I can always apply S to get 1S. And I can do this recursively at this recursive application. The goal here is I want to be able to take an unknown sentence, say for example this one, and tell me if these grammar rules can generate this sentence. Now the question is, why do we want to do that? Well, let's take a line of code. Say for example I have int x equals 3 with a semicolon. I want to validate that that is a correct sentence in C. How do I validate that this is a correct sentence in C? I have to be able to start with a generic C program, say S, apply some rules, and end up with that line of code. Not just C program, but a sentence in this case. How do I know if that's a valid sentence in C? Now, we go there, we go, okay, yeah, that's formatted correctly, so we're okay. Right? How do we do that in a computer sense? And that's what we're trying to solve here. And that's what context-free grammars, because I made the claim before that context-free grammars allow us to do this. And today what we're doing is, how do context-free grammars work to allow us to do this? And this is one method of applying it. Does that answer your question now? What we're trying to do? So I have this sentence, 0, 1, 1, 1, 0, 1, 1, 1, 0. And I want to see if I can make this sentence using this grammar. That's all I'm trying to do. And I'm trying to tell it, and I asked in the beginning, I said, can we prove that we can or cannot make that sentence?
We can prove.
We can prove, so let's take a different sentence. Let's take maybe an easier sentence. Let's start with just the sentence 1, 0. Can I make that sentence with this grammar?
Yes.
Yes, I can, right? I can prove that. How do I make that sentence with that grammar? I apply rule 1, so I start with the sentence S. I apply rule 1. When I apply rule 1, I get the 1 and the S, correct? Then when I apply rule 2, so this is rule number 1. When I apply rule 2, I get the 1 and the 0. And that is that sentence. That means this grammar, starting from an S, I can generate the sentence 1, 0. So this is a valid sentence. Can I prove that that is not a valid sentence? Or is this a valid sentence? Does anyone want to say that, yes, this is a valid sentence still? No. So this is not a valid sentence. Why is this not a valid sentence?
Because the only 0 we have is a terminator, so we cannot use it to start it, to make larger ones.
We cannot put a 0 on the left-hand side of a 1. Ever. Right? That's what this is. That's what we have here. We cannot ever put a 0 on the left-hand side of that 1. That's the reason why we can't generate this sentence. Now, we can inspect this, and we can be like, yep, good. Can't do that. Yes?
Are you going to use different numbers to signify the terminating value, like other than 0, other than
Say that one more time. I can't hear you.
Are you going to, for the pattern that we're going to try to make, is it always going to be zeros and ones, or the rules going to change? And, the symbols going to change?
So for this introduction, we're only going to use 0 and 1, simply because it's the easiest thing to think about. Then what we're going to do is we're going to look at some context-free grammar for C. And we're going to look at the rules for C, and then we're going to take a look at how C does it. And we can look at how C actually does the context-free grammar across the entire program, and how we can prove that a program is grammatically correct, including all of the sentences inside of it. Okay, so we know that we can prove this one, but how do we prove that we cannot generate that 0? So as humans, we're able to deduce, we can't put the 0 to the left of that 1. Can any of you write a computer program that can tell us that? No. Well, somebody might be able to eventually. Yeah.
Is this similar to that guy who like won proof for like x squared plus y squared equals z squared? So that's true, but he proved that it's impossible to do that with anything but the 2's.
So
It's hard, very
It's-
hard, like hundreds of years hard.
yeah, it's one of those things where the problem sounds super simple, but it's really not. This kind of mathematical proof is very difficult to do. You might be able to write a program that'll solve it in this single case. But let's add a third rule that still doesn't allow that to occur. How do you prove it in general? And that general proof is almost impossible. That's the part that's really difficult to do. So we don't have a general proof for proving how the 1s and the 0s can be organized. The only way that we know, there's 2 ways to do this, but the only way that we know how to do this, starting from the S, is to try all possible trees. And when we say try all possible trees, we mean the following. Because currently, we're just looking at applying the rules, like so, right? When we talk about applying all possible trees, we start with the same S at the top. Then we can apply rule 1. When we apply rule 1, we get a 1 off to the left over here, right? This is by applying rule 1. Off to the right, we're going to say that we have an S. If we apply rule 1 again, we get the 1 and an S. If we apply rule 1 again, we get the 1, we get the S. If we apply rule 0, or rule 2, sorry, we get the 0, like so. So this is a tree, right? We can see that this is the root of the tree. If you take a 310, this is much simpler as far as understanding this is a tree. This is the root of the tree. It has 2 leaf nodes, or 2 nodes in the bottom. One of them is a leaf. The leaf is a terminating node, right? A terminating symbol. Everything that's non-terminating is inside the tree. So all non-terminating symbols come down to the bottom. All terminating symbols come down to the bottom. All non-terminating symbols are on the inside. And so we can see that the S flows down on the inside, and then the terminating symbols make up the bottom. So this will apply rule 1, apply rule 1, apply rule 1, apply rule 2, we get that. Right? Another tree, for example, would be to take S and apply rule 1, apply rule 2, like so. That's another tree, correct? What about that's another tree. Those are all trees from this grammar rule over here. And we can see that the terminating symbols on the bottom are the sentences. Like so. Any questions about this part so far? Right? Let's consider how we can turn this into a validation of that sentence there. Start with the green one. If I start with the sentence S, and I apply rule 1, yes? 0 in the middle? We haven't even talked about doing that. Okay, we'll get there. That's a good question. All I'm doing here, I'm still just trying to validate or disprove this sentence. Is all I'm doing. We'll do other ones later. Yes?
And the trees don't have to be balanced, right? They just need...
Correct. There's no balance to the trees. All you do is you have the terminating ones as leaf nodes, and the non-terminating is the inside. And they can non-terminate for as long as you want them to, but eventually the terminations will all line up on the same line. Eventually everything will terminate. So if we apply rule 1, we know that this left-hand branch is going to go as far down to the left as it needs to go. Have a 1 here, with a non-terminating in the middle. This one on the left over here, yeah, that's the left for you guys. This one on the left, can I ever generate this sentence from this tree, regardless of what this S turns into? I cannot. How do I know that? Well, it's not just the rules. Can I ever get a non-terminating symbol to the left of that leaf node now? To the left of that terminator? I cannot. And so by looking at the tree this way, we can identify that comparing the leftmost guy here with the leftmost guy here, that those are not valid. Those do not match. Since those do not match, I cannot apply rule 1 as my first rule. Correct? So I know that by applying rule 1, so essentially what I do is I try all rules in all possible ways, and I try to match at every stage whether or not I can get there. So if I first, in my first stage, I say, hey, tried so far. Let's say the first time I tried it, I tried rule 1 as my first rule. I know that trying rule 1 as my first rule fails, so this does not work. It doesn't matter if I try any other applications afterwards, because I cannot generate that sentence. Right? Because I cannot generate the 1 to the 0. That doesn't match. So now I'm going to try my second set of things to try. So I'm going to start with my sentence S up here. And what can I start with if I don't start with 1? I can start with rule 2. But, I mean, if I don't start with rule 1, I can start with rule 2. So I'll start with rule 2 now. By applying rule 2, I get the following. Does this match that 0? Yes, it does. Okay, so now I'm going to move on to my second step. So I applied rule 2. I'll move on to my second step and try to apply more rules. Can I apply any more rules? No, I cannot. That means I'm done generating this sentence. And now I can verify whether or not this entire sentence matches that entire sentence. Does this entire sentence match that entire sentence? It does not. So what does that mean? I can't generate it with my second attempt. Right? So that means I have now exhausted all possible attempts. My attempt A and my attempt B. There are no other possible attempts that I can try to generate this sentence with. So I'm now done and I cannot generate this sentence, therefore that sentence is invalid. Questions about that? All right, so now we're going to do one with a 0 in the center. Okay? Let's try 1, 1, let's do 1, 0, let's do 1, 1, 1, 1, 0, 1, 1. Let's try that. Let's try to validate that sentence using these rules. So what I want you to do is I want you to systematically apply sets of rules and identify which sets of rules you're applying each time and the orders that you're doing. So for example, tried so far, what is the first set of rules that you apply before you realize that it fails or doesn't fail? So I'm going to tell you right now, we cannot generate this sentence. This is an invalid sentence. Yes?
The first one is 1, 1, 2.
So it's not even necessarily 1, 1, 2. It's actually going to be a different one. It's going to be 1, 1, 1, 1. Apply rule 1, apply rule 1, apply rule 1. The second one we're going to try is 1, 1, 2. Right? So we apply 1, 1, 1. When we apply 1, 1, 1, we get S, 1. Does that 1 match that 1 up there? So that means I can continue from this point. So I try the next one. So I try my first rule again. Give me the 1. Yes? Do these both match the first two? Oh, good. So now I'm going to try my rule 1 again. And does that match that up there? That does not. That means that this fails at that third application of 1. Is that right? Yes. So now I want to try my second one. So I'm going to try my second one. So when I try my second one, what I do is I step back from my last failure, which is this guy right here, and I try my other rules. So what I'm doing is, so now I'm still at 1, 1, and now I'm going to try my 1, 1, 1, 2. This is not the values, this is the application of the rules. Maybe we should call these, maybe I should switch this from A to A, rule A, rule B. Would that be better? Yeah. Yes? Would that help someone? No? Let's do it that way. Maybe it'll make a little more sense. We'll do rule A and rule B. So this is our
Case 1.
this is our first attempt, and this is our second attempt. So we do A, and we find out that we fail on this one here. And so we try to do rule A. We try our other rules in our third slot here, so we get the second rule B, or rule B. We apply that. And when we do that, and when we apply our other rule B, that means that this one doesn't become that, it becomes this. So we say, great, so the 1, 1, 0 matches, but now can we apply any more rules? And the answer is no. So we take that entire sentence, we go, is that entire sentence that entire sentence? No. So that fails. So we fail this B. So now I try our third attempt. And our third attempt is going to be the same ones as before. We try our other rules. Are there any other rules to try?
No.
This one? No. So what I do is I back off, and I look at this one now. So I try instead of A, I try B. What I'm doing here is I'm doing a permutation of every possible rule application.
Why?
Hmm?
Why?
Because if a rule application will succeed, it will be a permutation of the rules. That's guaranteed. Because I can apply the rules in an infinite number of ways, but if there's some number of rules that are going to be applied, so for example, AAA doesn't work, so maybe AAB does. But if AAB doesn't work, that means I have to step back and try ABA, because maybe ABA works. Or ABB, or ABAAAC. I don't know that yet.
I think not what we do.
Hmm?
It has worked to the point, and we got to the point where it works, and we don't have to change anything of that. And then we only have 2 options, so we've already exhausted all the possible options.
Correct, but that's still developing a permutation. Then by definition, the permutation is exhausting all possible options.
We already did in 1 and 2.
I'm sorry? This one here? No, we haven't. Because what if I did AB? What if AB worked?
And then we failed.
Do you know that AB works or not yet?
And,
You know that it doesn't. Why?
but it failed.
Because you tried it already.
No.
Simply because you tried it doesn't mean that the computer's able to try it yet. So one of these things is, as humans, we're able to look at this AB and we generate that tree in our heads and go, that doesn't work. And that assumption that we've been able to do that, that a computer can do that, isn't true. The computer has to try it because the computer doesn't know how to do it by intuition. We don't know that AB doesn't work. Because we can't do a general purpose, let's put the 0 to the left of the 1. We don't know that. We can't prove that. So we do the S. With this one here, we get the tree that doesn't work. Right? We find the 1 and the 0 that doesn't work. That means that one's going to fail. So we do our 4th attempt. This is actually what we do when we solve this problem. We do all the permutations. We just discard them in ways that are intuitive to humans. Computers don't have intuition. That intuition where you say, but I know it's not going to work, isn't true for computers. Computers don't know that. You have to try them all. So in this case here, I'm going to try B. And then when I try B, B is going to fail as well. And then all my cases are going to fail. And I've tried all possible permutations that could work, and that will fail. Any questions about this? So what I want to do is I want you to try to figure out how do we change these rules such that this one will succeed.
0S.
So we'll have a 0S. Like that? So we'll try it with a 0S. Now this is an interesting problem. Let me put it as green so we know it's the center.
Can we create new rules, or do we?
Yeah, you absolutely can create new rules. Yeah.
And new S is equal to 0.
So as S equals to 0?
Yeah, C.
Ah. Okay, so before we add this to the third case, which we will need, we will absolutely need the third case. This fails. This fails all cases. Why does this fail all cases? It never stops. And so we have to have some form of termination. So let's add a C rule. We'll say S goes to 0 or 1? 0? So let's go S goes to 0 first. Does this rule succeed?
No.
No, because other people were saying S goes to 1, you went, shit, I did it wrong. It's okay. When we're looking at this, why does S goes to 0 doesn't work is because after we apply these 1s, after the 0, we have to be able to apply that 0 at the end, and we don't want to have a 0 here, so that doesn't work. However, the S goes to 1 does work. S goes to 1 does work because that can be the last application there. The other thing we can do is we can say S goes to nil, and nil means nothing. It just disappears. So when we say S goes to nil, the terminating character nothing, the terminating character just disappears. That would also work in this case here. And the tree that we would generate for this would be something along the lines of, let's try it. What would generate that sentence? There might be multiple trees that will generate this sentence, but let's try Let's try 1. We do this. We go apply rule 1. We get 1. S. We apply rule 1. We get 1. We get the S. We apply rule 2. We get the 0. We get the S. Apply rule 1. The S. Apply rule 1. Get the S. Apply rule 3 or C in this case here, and we get nil. And so this comes off to nothingness, not a space, just nothingness. And then we say, hey, does this sentence equal that sentence? The answer is yes, it does. Now, is there more than one tree that generates that sentence using those rules? No is a good answer. All right, let's do something else. Let's take that S, stick it on the right hand or the left hand side. Now that's the rule. Is there more than one tree that generates that sentence? Because that tree, these rules will generate that sentence. Or is that true? Is that false? Actually, that might not be true. That tree might not generate that sentence. No, nil would just disappear. When nil is in the middle, it just disappears.
Could be like, no, like doesn't, because we always have a 0 at the right, and we keep putting s's in the middle. We keep expanding with the s's in the middle.
In this case here, that 0 can be off to the right, and that 1 can be off to the left, but we can't get zeros to the left of the 1s still. We can't get 1s to the right of the 0 with this logic here. Even with the nil, we can't do that. So this doesn't generate that sentence. Can you come up with a rule that will generate this sentence, but does not generate, or a set of rules, but does not generate that sentence? So it generates this sentence, but does not generate this sentence. So yes on this one, no on this one. Yes. So S 0, 1, 1 is what you want? Or why not just 0, 1, 1? Does that work too? That's a good rule, right? Do I need rule C for this one? I don't need rule C. That's kind of cheap. There's an even simpler one. Want to see the simple answer? S goes to 1, 1, 0, 1. Right? That's the easiest answer. Like so. Now can you generate a sentence structure that'll generate either one of these here? Neat. Right? Now, are these rules useful? No. Can you generate it with a smaller, with a subset that generates those two sentences and an infinite number of other sentences as well that are similar? Well, let's make it harder. So you can't use these two. You have to use something less specific. So 1S, 0S, and then we had C, which was S goes to 1. Does that work? Do you mean S goes to 0, or does S goes to 0 work for us? S goes to 0 should work. What would be the rules to apply to generate that sentence? Right? So A would generate the 1, the B would generate that one, the A, and then the nil to terminate. Right? This one over here, we would do B, A, B, terminate. Can you make a set of rules that would generate both of these sentences in multiple ways? Both sentences can be generated with multiple trees. And then what are those two trees? Or more than 2. It doesn't have to be exactly 2, but at least 2 trees. Both sentences have to be generated with multiple trees. So you're saying add 2 more rules?
Yeah, instead of C go to 1, like S goes to 1, and S goes to 0.
Okay, so we'll say that C can be S goes to 0, and I'm going to use a bar here, which is like a pipe. That pipe, that pipe means either one of those. It can be either one of those rules. We could actually write all of these rules on a single rule. Like, so for example, we could say S goes to 1S or 0S or 1 or 0. That's all still the same. Those are the same rule set. Yes.
We usually only have one S.
What do you mean?
Like,
One non-terminating symbol?
Yeah,
No, we have multiple, many.
here.
We have lots. And so you could definitely use other non-terminating symbols. Particularly when we do this for actual languages, we have several non-terminating symbols.
So why call them AS, BS, CS, not only A, B?
So we could also have T's, we could also have X's, we could have all
So
kinds
what
of.
way we could do this?
So use other letters. Like, so say S goes to 1T and T goes to 0S kind of deal. You could do that as well. And what that does, so for example, if I say, if the rule is this way, S goes to 1, that's in 1 again, sorry. 1T and T goes to 0S like that, can I generate either of those sentences? I cannot. Why can I not generate either of those sentences? I can't repeat once. Because if I apply, so if I start with rule S, let's start with rule S to start. And so when you do this, you have to start with rule S. Now we also have to start with rule T. We have to try both starting places as well. Every time you add a new non-terminating symbol on the left, you have to start with a new non-terminating symbol in your tree generation as well. So if I start with S, I can generate 1 T, which can generate 0 S, but I can't ever get 1 1. If I start with T, I can get 0 S 1, but I can't get 2 zeros in a row. Right? So you can absolutely do that as well. So that won't generate any of our sentences, so let's try this again. So we get 1 S, and then S goes to 0 S. And you're saying S goes to 0 1 would generate both of these in multiple ways? That's the claim?
Do we have a D that S goes to
Sorry?
1? Do we have a D S goes to 1?
Yes, we can. So if you so before we add the D, can we generate with multiple ways with those 3 rules? No, there's only one generation for each of those trees. Why is that? There's only one. If we add in the third one, S can also go to nil. Now we'll have multiple trees. So for example, the 1101, if we start with S, 1 S 1 S 0 S 1 S 1 S nil, right? Or we could do S 1 S 1 S 0 S 1 S 1. Those are 2 different trees generating the same sentence. Can you make an English sentence that has 2 different meanings based upon 2 different grammatical applications? So, can you make an English sentence that has 2 different meanings based upon 2 different grammatical breakdowns of that sentence? So what would that be?
So if we say like,
look at the butterfly floating through the flower.
The butterfly floating through the flowers, right? What are the two grammatical breakdowns?
Either the man is floating through the flowers
Or the butterfly is floating through the flowers. We can have, because this sentence is grammatically correct in two different ways. One where the grammatical floating through the flowers is the butterfly, and one for the floating through the flowers is the man. Excellent job. I know that's a strange sentence, but it's good. Is there a simpler sentence that is the same thing? Probably. I don't know it off the top of my head, but that was a good one. So yes, absolutely. Doesn't matter which one of these grammars we choose to validate the grammatical correctness of the sentence.
Yes. Because that's ambiguous, so you cannot have it.
So this is ambiguous semantically. It's not ambiguous grammatically. Ambiguous semantically is it means something else. And so that's, as far as we're concerned, when we're doing context-free grammar analysis, we don't care. If it is grammatically correct one way, it doesn't matter if it's grammatically correct another. All we want to know is it grammatically correct. Later, semantic correctness is determined by the code emitter or the interpreter. If the code emitter or the interpreter can't disambiguate between the two of them, then that will fail, not the grammar stuff. Kind of like here, does this sentence mean nothing to you? It just changes its meaning depending on how you choose to interpret it. So when you have a programming language, you can have a programming language that chooses to interpret it as the participle over here, this part over here, always applies to the subject, or this participle always applies to the object. And you choose your language to apply one way all the time, and then it doesn't matter that the grammar is inconsistent. It's always applied in the same way. Okay. What time is it? Let's take a look at context-free grammar for C. Let's see if we can take anything. See if we can find a good one. I know there's a really good one, I just don't remember what the URL is on the top of my head. So this is one way we can look at them. So for example, this is the tokenization step. And what we're defining on the left-hand side over here are the S's and the T's, for example, which would be the non-terminating symbols or the terminating symbols. So for example, assignment operator is actually equivalent to any one of these symbols or sets of symbols. And so when our tokenizer goes through this assignment operator, it's going to find that equal sign and say, hey, that's an assignment operator. And so we can see that this guy here is also an assignment operator. Now the fact that this assignment operator is different than that assignment operator doesn't matter until we're actually implementing it. So for example, the difference between plus minus and minus, or plus equals and minus equals, Doesn't matter until we try to actually look at it grammatically. So for example, if we have the code x plus equals 3 versus x minus equals 3, grammatically we want to treat these symbols in the center as the same thing. Because grammatically that symbol doesn't matter yet. Semantically they're important, but grammatically they're not. And so what we're going to say here is we say, hey, these two things are the same kind of object, or the same kind of part, as they are here. We call them the assignment operator. The assignment operator. Let's go see if we can find some more of them. Here's another expression. Here's an assignment expression, or an assignment followed by an assignment expression. So when we talk about, so this actually might be the actual rule here in this case. That this turns into an assignment operator. An expression, let's use the capital E instead. When we're looking at this, when we're trying to read this, what we're saying is we want to say E, an expression, can become either an assignment expression. Let's do an AE for assignment expression. Or E can become an expression followed by an assignment expression. Either one of those things are acceptable. Let's see if we can find the assignment expression declaration. When we find this one here says the assignment expression is either a conditional expression or it's a unary expression. Unary expression followed by an assignment operator followed by an assignment expression. Those three things in order. If we look up unary expression, unary expressions can be any of these things. Looks like they might also be more. So it could be any of those things. Postfix expression. And so we look at a postfix expression, we can find where eventually we'll get. Eventually what happens is this all bubbles up to the top where we get to the part where we say we have a declaration or we have a value of something. Let's look at postfix expression and see if we can find that. So a postfix expression is a primary expression, or a postfix expression with calling a function with an argument list inside of it, or a dot identifier, or an arrow identifier, or a plus plus, or a minus minus. So if we look at primary expressions are identifiers, constants, string literals, and expressions. And so when we talk about, hey, the identifier, for example, x, is a primary expression. So when we start, when we see the letter x, that's an identifier. If we want to validate that x equals 3, like so, probably don't have a semicolon in it at this point. We want to validate that this is a grammatically correct sentence. We start at the primary, we have the x is the identifier, which is a primary expression. The primary expression can become the postfix expression. The postfix expression gets used down here as part of the unary expression. That unary expression becomes part of the assignment expression, which includes an assignment operator, which is one of these symbols, which happens to be there, so that's an assignment operator. And then the 3 probably is assignment expression. Well, we already did the assignment expression. Oh, so it's itself again, should be the unary guy at the top of here. Yes? No. And so the way I did this one here, I didn't do this one by starting at the top and working our way down. What I did is I started at the bottom and I worked our way up. So the way that we talked about how to do this sentence generation for languages and context-free grammars, this is called a top-down grammar rules. And writing top-down parsers or top-down context-free grammar is difficult. In fact, it doesn't work. Primarily or particularly when you have this many, I don't know, that's probably 100 or so non-terminating rules on the left-hand side. And so when you have the 100 of them, you have to try every single possible version of them. When you have to try every single possible version, all permutations of them, that can take forever. It's an exponential problem when you're doing that permutation across the tree of all of them. So we don't want to have to do that with C, or with any programming language for that matter. What we do is instead we do a top or a bottom up parse. So I just threw that word up. This is called parsing. This is what parsing is referred to as. Instead of doing a top-down parse, which is what we've been doing so far, you want to do a bottom-up parse. Or this is also sometimes called an LR parse, for left-right. So we want to do an LR or a bottom-up parse. Let's assume a simple set of rules again, and a simple tree, and a simple sentence to validate. Let's say that we have rule A is S becomes 1S again, and rule B is S becomes 0, just the super simple sentence, super simple generation. And I want to be able to validate the sentence 1, 1, 1, 0. Now that I can generate that, correct? The way that we're now doing this, how did you figure that out? That we can generate this sentence using these rules? Intuition. So let's break that intuition down. How did you actually look at this? What was the first thing you looked at? Did you look at the A, the B, or the 1? So you started on the 1 here. Did you look at the 0 first? No? So if I hid something here, can we generate that? Did you look at the 2 or the 7s? Do they matter? No, all you care about is that 0. What we're doing here is we're going to start on the left, and we're going to work our way right to parse these. And this is the reason why we call it an LR, or a bottom-up parse. LR stands for left-right. What we do is we start from the empty sentence. So let's suppose we have the empty sentence. We have nothing to start. Which of these rules could we apply such that we get the next value correct? Could we apply B? So if we applied rule B, would we get the correct sentence? And so from the left-hand side, is the first character 0? It is not. So we know that B is not the correct rule to apply. What rule do we want to apply?
A.
A. So when we apply A, we'll get a 1 there. And by starting on the left-hand side, we know that we're going to generate this tree by applying rule number 1. Like so. And with rule number 1, I know that I get an S here. Now, which of those rules can I apply?
A.
One, or A or B, right? I can apply rule A or I can apply rule B. If we had a third rule here, C, T becomes nil. Let's say T becomes nil, and this is 0T, like so. Can I apply rule C? Why can I not apply rule C?
There is no T.
I do not have a T in my parse tree available for me to use. This S has been used, this S has not been used, and so I don't have a T to use. Let's apply a rule, so I'll apply rule A again. Rule A, not rule 1 again, sorry. Rule A, which will give me that 1. Is this the correct, am I good so far from the left-hand side?
Mhm.
I am, so I'll continue. So I'm going to look for the next one. When I applied rule A, I also got the S there. Now I'm going to try and apply rule A. By applying rule A, I would get a 1 there. By applying rule A. Is that valid?
No.
Is this 1, 1, 1 what I want?
Nope.
It is not, so I don't apply rule A. Now I apply rule B. When I apply rule B, I get a 0. Is that correct?
Mm-hmm.
Right? Which allows me to, which brings me down to, this one comes to a T when I apply rule B. Now when I have that T, I know that T can go to nil, but I start off by applying rule A. And I look here, and that would put me a 1 there. Is that valid? No. Actually, I'm sorry. Can I apply rule A?
No.
No. Can I apply rule B?
No.
No. Can I apply rule C?
Yep.
Yes. So I can. So I can apply rule C, so I get the nil for rule C, so I have the nil in the beginning and the end, and I have the final sentence, and that's valid. So it allows me to validate this. This is called a left-right parse. So instead of starting at the top and then choosing all of my rules and then failing as we go down, like failing at the end and then backing off, I start on the left-hand side and work my way forward. You can also do this by doing from the right to the left-hand side if you wanted to, but usually we talk about left to right parsing. They're identical. Right-left parsing, left-right parsing are the same. But we talk about left-right parsing because most sentences are constructed in a left-to-right manner in English. If you happen to speak a language that is right to left, or up to down, or down to up, as opposed to left to right as your native language, this might not be as intuitive to you, but for left to right speakers or readers, that's the most intuitive way to think about it. So this is the left-right or the bottom-up parse. We start on the left-hand side, we generate our tree. Go ahead and generate the tree. Let's do what does the parse tree look like for that left-right parse before it fails? So when we're doing it left to right, I'm going to start on the left-hand side. So I have I can either start with S or T. I don't have you can say that we have a blank rule up here where if nothing, I can be either S or T. So I can go to S or T from nothing. So what's the first? So write the entire tree out. Everybody write the entire tree out, and I'll write it out, and then figure it out. This is the letter 0, sorry. Number 0. What's the tree look like? So we know that we want to start here. We're going to have a 1 first. That's going to be the first thing we're going to find. Which of those rules do we apply? We know that we're going to apply rule A, which means that we're going to get the S on top, which goes down like so to the T. Now when I'm here, which of the rules can I apply? And the answer is going to be B. So I get the 1 with the S. This is going to be way too big. S to the T, the S, which allows me to apply rule 1. Now, I don't have to worry about applying rule C yet because it's not going to fail yet. Or is it going to fail? I'm going to get to, that's going to give me the T, which will give me the 0, right? Yeah. Yes. 1, 0, 1, 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
And C for me.
So now I'm at this stage here where I have this T guy hanging off, and I need to generate the next character. Now the next character that I need to generate is nil. Can I generate nil from T?
No.
I cannot. So this guy would fail. And we would be able to come back to here and we'd say, hey, is there a different thing we could generate other than from S other than 1? And I could try to generate nil. And when I generate nil, that sentence is invalid. It no longer works. And so I failed that sentence. I could go back through and I could try each one of these, and I know that each one of these is going to fail as I come back out through my parse loop. So I parse left, and then I come back right as I fail, and I go left again. The goal here is with a left-right parse or a bottom-up parse is complete the grammar as quickly as possible, if possible, and the easiest way. And so it's the most likely you're going to be able to complete the grammar on the first try if it's grammatically correct. Let's do as a secondary one. Let's go ahead and try to generate. Oh, we'll just use this one. Let's generate some rules that are going to turn some very standard C expressions into validating that they're grammatically correct. So, for example, if I have the C expression x equals 3 plus y, I want to validate that as a grammatically correct sentence. So let's generate a set of rules that allow that to be validated. Right? If you want, you can start by saying that all these guys are just identifiers. So instead of x, it's really identifier x and identifier y, and identifiers are known as identifiers. So what would be a rule or a set of rules that validate that sentence as correct? Like some rules that would do that. What would be some rules that validate that sentence? The simplest one
X equal to 2 plus 1.
So the simplest one would be like, hey, the sentence identifier, let's say ID equals sign number plus ID. Let's say all numbers can be numbers like that. That'd be the simplest rule that would validate that sentence, right? Wouldn't validate any other sentences though. Is there a set of rules that allow us to validate that though? So you can say ID goes to ID assignment. I'll just use A for assignment here, like that. So if this was the first rule we had, if I started with ID and I did this, I would get ID and the assignment operator, so an equal sign. Can I get anything to the right of the assignment operator here? So that wouldn't be able to validate this part here. Because I'd have the ID with nothing to the right of the equal sign.
What if you were to do like also assignment goes to assignment constant?
So you're saying assignment, so assignment goes to the word assignment and a constant, some sort of constant value. So a constant.
But then the constant goes to constant expression constant. Without word.
So a constant could also, so you have,
I don't know if it'd be like also a variable.
Yeah.
I don't know if word also contains constant or variable.
what if we did something more like an expression? Because this, what is this whole thing? Right? Like, is this substantially different than this? Are those two substantially different? X equals, or x assigned 3 and x 3 plus x. What's the difference between these two? That thing in the center, right? What's this thing in the center? What's the commonality between the two of these? They're both operators, right? So what if we said something along the lines of expression can be, what's this thing and what's that thing? What are those two things?
Constant and variable.
So that's a constant and a variable. What's common between constants and variables? So 3 is not an identifier where x would be an identifier, right? But they're both values, right? We don't necessarily know the values, but we could say, hey, an expression can be a value. So we'll say value, operator, value. So an expression can be a value, operator, value. Right? A value, for example, 3 plus x is also a value, correct? The result of 3 plus x is also a value, so a value can also be an expression. Then we can have something along the lines of an identifier can become a value, and a number can become a value. So we're saying identifiers can become values, numbers can become values, values can become expressions, and expressions are values, operators, values. Does that validate that sentence there? The number would be the 3. So some literal value. So instead of value, if you don't want to have a number, you can say literal value. A literal value can become a value.
Would it be value to literal value? Just because I'm wondering.
Like how we level like 3 is equal to 4.
So okay, so the question is this sentence here, right? That's a sentence that shouldn't be validated. It's grammatically correct, but according to this, it is grammatically correct. Is what you're saying, right? That is true. That grammar also validates this sentence. This sentence and this sentence are both grammatically correct according to that structure over there. So this doesn't exactly mean what we want to be able to do. Value, operator, value isn't exactly it. There might be a little bit more, but we'll have to figure out that. Let's figure out what that is in this. No, we don't have time today. But we can figure out a different way to think about how to do that value, operator, value later as we go through. That's part of the reason why there are so many rules when you look at the rule tree for those context-free grammars for C, because you have to figure out how to differentiate the left-hand side of the equals operator versus that guy. Because operators are not necessarily just operators. If we just want to validate this sentence, this is fine. But if we want to be able to disallow that sentence that is not fun. And that's the difference between the two. So for example, if we did it this way, we could say, maybe this wants to be an expression can become a value or something along those lines. But we would have this guy, this guy here is essentially a value operator value, so that would become the expression. And then we have a value here with an operator. So this one would be backwards. The expression can be a value, which means that we have value, operator, value, which would turn that into an expression. And we validate that from all the way up there. That's a tree that would generate it. Because that's an expression, value operator, expression, value operator, value, expression. But that grammar also validates the thing we don't want to validate. So you have to think about how do you fix that. You have to have a different set of rules to make sure you disallow what is not good while you allow what is good. So context-free grammars aren't simple. There's lots involved, but that's it for today. Have a good spring break. You're done.